Hello, class. In this chapter, we're going to learn about the electric charge and electric field. Looking ahead, these next few chapters will develop the ideas about electricity as well as its relation to magnetism. The word electricity comes from the Greek word electron, which means amber. Amber is a petrified tree resin, and the ancients knew that if you rub a piece of amber with a cloth, the amber attracts small pieces of leaves or dust. A piece of hard rubber, a glass, or a plastic ruler rubbed with a cloth will also display this amber effect, or static electricity as we call it today. You can readily pick up a small piece of paper with a plastic comb or ruler that you have just vigorously rubbed with even a paper towel. You have probably experienced static electricity when combing your hair or taking a synthetic shirt from the clothes dryer. And you may have felt a shock when you touch a metal doorknob after sliding across a car seat or walking across synthetic carpet. In each case, an object becomes charged as a result of rubbing, and it is said to possess a net electric charge. Is all electric charge the same, or is there more than one type? In fact, there are two types of electric charge. As the following simple experiment shows, a plastic ruler suspended by a thread is vigorously rubbed with a cloth to charge it. When a second plastic ruler, which has been charged in the same way, is brought close to the first, it is found that one ruler repels the other. This is shown in Figure A. Similarly, if a rubbed glass rod is brought close to a second charged glass rod, again a repulsive force is seen to act, as shown in Figure B. However, if the charged glass rod is brought close to the charged plastic ruler, it is found that they attract each other, as shown in Figure C. The charge in the glass must therefore be different from that on the plastic. Indeed, it is found experimentally that all charged objects fall into one of two categories. Either they are attracted to the plastic and repelled by the glass, or they are repelled by the plastic and attracted to the glass. Thus, there seem to be two and only two types of electric charge. Each type of charge repels the same type but attracts to the opposite type. That is, unlike charges attract and like charges repel. The two types of electric charge were referred to as positive and negative by Mr. Benjamin Franklin. Franklin argued that whenever a certain amount of charge is produced on one object, an equal amount of the opposite type of charge is produced on another object. The positive and negative are to be treated algebraically. So during any process, the net charge and the amount of the charge produced is zero. For example, when a plastic ruler is rubbed with a paper towel, the plastic acquires a negative charge and the towel acquires an equal amount of positive charge. The charges are separated, but the sum of the two is zero. This is an example of a law that is well established. The law of conservation of electric charge, which states that the net amount of electric charge produced in any process is zero. Or said in another way, no net electric charge can be created or destroyed. Only within the past century has it become clear that an understanding of electricity originated inside the atom itself. A simplified model of the atom shows it has a tiny but massive positively charged nucleus surrounded by one or more negatively charged electrons. The nucleus contains protons, which are positively charged, and neutrons, which have no net electric charge. All protons and all electrons have exactly the same magnitude of electric charge, but their signs are opposite. Hence, neutral atoms have no net charge, containing equal number of protons and electrons. Sometimes an atom may lose one or more of its electrons, or may gain extra electrons, in which case it will have a net positive or negative charge, and it is called an ion. In solid materials, the nuclei tends to remain close to fixed position, whereas some of the electrons may move quite freely. When an object is neutral, it contains equal amount of positive and negative charge. The charging of a solid object by rubbing can be explained by the transfer of electrons from one object to another. When a plastic ruler becomes negatively charged by rubbing with a paper towel, electrons are transferred from the towel to the plastic, leaving the towel with a positive charge equal in magnitude to the negatively charged acquired by the plastic. Normally, when objects are charged by rubbing, they hold their charge only for a limited time and eventually returns to its neutral state. Where does the charge go? Usually the excess charge leaks off onto water molecules in the air. This is because water molecules are polar. That is, even though they are neutral, their charge is not distributed uniformly, as shown in the figure. Thus, the extra electrons on, say, a charge with a plastic ruler can leak off into the air because they are attracted to a positive end of a water molecule. A positively charged object, on the other hand, can be neutralized by transfer of loosely held electrons from water molecules in the air. On dry days, static electricity is much more noticeable since the air contains fewer water molecules to allow leakage of charge. On humid or rainy days, it is difficult to make any object hold a net charge for long. Suppose we have two metal spheres, one highly charged and the other electrically neutral. If we now place a metal object, such as a nail, so that it touches both spheres, the previously uncharged sphere quickly becomes charged. If instead we have connected the two spheres by a wooden rod or a piece of rubber, the uncharged ball would not become noticeably charged. Materials like the iron nail are said to be conductors of electricity, whereas wood and rubber are non-conductors or insulators. Metals are generally good conductors, whereas most other materials are insulators, although even insulators conduct electricity very slightly. Nearly all natural materials fall into one or the other of these two distinct categories. However, a few materials, notably silicon and germanium, fall into an intermediate category known as semiconductors. From the atomic point of view, the electrons in an insulator material are bound very tightly to the nuclei. In a good metal conductor, on the other hand, some electrons are bound very loosely and can move about freely within the metal, although they cannot leave the metal easily, and are often referred to as free electrons or conduction electrons. When a positively charged object is brought close to or touches a conductor, the free electrons in the conductor are attracted by this positively charged object and moves quickly towards it. If a negatively charged object is brought close to the conductor, the free electrons in the conductor move swiftly away from it. In a semiconductor, there are many fewer free electrons, and in an insulator, almost none. Suppose we have a positively charged metal object A is brought close to an uncharged metal object B. If the two touch, the free electrons in the neutral one are attracted to the positively charged object, and some of those electrons will pass over to it. Since object B, originally neutral, is now missing some of its negative electrons, it will have a net positive charge. This process is called charging by conduction, or by contact, and the two objects end up with the same sign of charge. Now suppose a positively charged object is brought close to a neutral metal rod, but it does not touch it. Although the free electrons of the metal rod do not leave the rod, they still move within the metal towards the external positive charge, leaving a positively charged at the opposite end of the rod. A charge is said to have been induced at the two ends of a metal rod. No net charge has been created in the rod. Charges have merely been separated. The net charge on the metal rod is still 0. However, if the metal is separated into two pieces, we would have two charged objects, one charged positively and the other charged negatively. This is charging by induction. Another way to induce a net charge on a metal object is to first connect it with a conducting wire to the ground, or conducting pipe leading to the ground. The object is then said to be grounded or earthed. The earth, because it is so large and can conduct, easily accepts or gives up electrons. Hence, it acts like a reservoir for charge. If a charged object, say negative this time, is brought up to the metal object, free electrons in the metal are repelled, and many of them move down the wire into the earth. This leaves the metal positively charged. If the wire is now cut, the metal object will have a positive induced charge on it. If the wire is cut after the negative object is moved away, the electrons would all have moved from the ground back into the metal object, and it would be neutral again. Charge separation can also be done by non-conductors. If you bring a positively charged object close to a neutral non-conductor, as shown in the figure, almost no electrons can move about freely within the non-conductor, but they can move slightly within their own atoms and molecules. Each oval in the figure represents a molecule, not the scale. The negatively charged electrons attracted to the external positively charged tend to move in its direction within their molecules. Because the negative charge and the non-conductor are near to the external positive charge, the non-conductor as a whole is attracted to the external positive charge. An electric scope is a device that can be used for detecting charge, as shown in the figure. Inside a case are two movable metal leaves, often made of gold foil, connected to a metal knob on the outside. If a positively charged object is brought close to the knob, a separation of charge is induced. Electrons are attracted up into the knob, and the leaves become positively charged. The two leaves repel each other, as shown, because they are positively charged. If, instead, the knob is charged by conduction, meaning touching, the whole apparatus acquires a net charge, as shown in figure B. In either case, the greater amount of charge, the greater the separation of the leaves. Note that you cannot tell the sign of the charge in this way, since negative charge will cause the leaves to separate just as much as an equal amount of positive charge. In either case, the two leaves repel each other. An electric scope can, however, be used to determine the sign of a charge if it is first charged by conduction, say negatively, as in figure A. If a negative object is brought close, as in figure B, more electrons are induced to move down into the leaves, and they separate further. If a positive charge is brought close instead, the electrons are induced to flow upward, so the leaves are less negative, and their separation is reduced, as shown in figure C. The electric scope was used in the early studies of electricity. The same principle, aided by some electronics, is used in much more sensitive modern electrometers.